Hello everyone, my name is Amar Koduru, and today I will be explaining about digital logic gates and universal gates. Now let's start with what is a logic gate. A logic gate is an electronic circuit that consists of one or more inputs and one output. It means that this circuit takes one or more inputs and just gives us one output. The relationship between the input and output is based on a certain logic. Since these gates are capable of performing these logics, they are given the name as logic gates. By interconnecting various logic gates, we can implement and perform various Boolean functions. Now, what is the purpose of the logic gate? In digital electronics and computer design, the logic gates are fundamental components used to perform various operations from binary inputs, such, such as ones or zeros. They are building blocks of digital circuits and they play a key role in design and functioning of various electronic systems, including computers. The basic, let's start with the basic logic gates, which are AND, OR, and NOT, with inclusion of buffer gate. These are used to perform and implement various Boolean functions. And we will talk about universal logic gates too, which consist of four gates, which are NAND, NOR, XOR, and XNOR gates. Let's start with the basic digital logic gates. And the first one we will be discussing about is the AND gate. The AND gate produces the AND logic function, that is, the output is 1 if input A and B are both equal to 1, otherwise the output is 0. The algebraic function is same as normal multiplication. We use either dot or nothing in between the variables. Now let's observe the circuit diagram for the AND gate. We can see that in the primary diagram, A and B are taken as inputs and we get the Y as an output. Now by observing the Boolean expression, as mentioned before, it is said that dot or space in between the variables, which means the inputs A and B, that's the representation of the AND gate. And now let's talk about the truth table of AND gate. It is also mentioned before that if it consists of both inputs, which is A and B as one, then the output would be one. In all other cases, the output would be zero. Now let's talk about the OR gate, which is also a basic digital logic gate. Like AND gate, the OR gate may have two or more inputs, but only one output. If this output is 1, if input A or B or both A and B are 1, otherwise the output is 0. The algebraic function is same as arithmetic addition. The symbol used for OR function is plus. Now let's observe the circuit diagram. Here A and B are inputs and Y is the output. And by seeing the Boolean expression, we can identify that in between the variables A and B, there's a plus symbol, which signifies the OR gate. Now, let's come to the truth table of the OR gate. As it says before, if both the inputs are 0, then the output would be 0. In case one input or both the inputs consist of 1, then the output would result in 1. Let's talk about NOT gate, which is another basic digital logic gate. The NOT gate is also known as the inverter gate, because the output is a complement of the input signal. The NOT gate inverts the logic 0 to logic 1 and logic 1 to logic 0, which means what it does is basically it complements the input. It has only one input and only one output. This is the main point which we will be talking about. Let's look at the circuit diagram over here. We can see that there is only one input, A, and we are only getting one output, Y. Now the Boolean expression, Y is equals to A bar. The bar here represents a complement of the given input, which is A would be equal to Y if it is a complement of A. Truth table of NOT gate. If the input side consists of 0, then the output would be 1. And if the input side consists of 1, then the output would result in 0. Buffer gate. It is also one of the basic digital logic gates. A buffer does not produce any particular logic, and this circuit is used only for power amplification purposes. Suppose you give an input 0, then the output for the buffer gate would result in 0. If you give 1, then the output would also result in 1. Its only purpose is power amplification. That's it for the basic digital logic gate. And now we'll move on to universal logic gates. And we'll start off with the NAND gate. The NAND gate is a combination of the AND gate followed by the NOT gate. That means the output of the NAND gate is equivalent to the output of the AND gate followed by the NOT gate. The NAND function is a complement of the AND function. This is the main point to remember the NAND gate. The first circuit diagram is of the NAND gate, which has two inputs, A and B, and of one output, which is Y. Uh, there's a pretty similarity. There's a big similarity between the NAND gate and the AND gate, which is the circuit design is pretty much similar. Only there's a bubble on the output side that represents the NOT gate. As it is said before, the AND gate followed by a NOT gate. So the circuit diagram is also pretty easy to remember. And now let's talk about the truth table. There's also a comparison between the AND gate and the NAND gate so that we can identify what it means. In the second statement, we said that the NAND function is a complement of AND function. If you observe the truth table, you will understand what's the meaning and the purpose of the above statement, which is what is the primary function of the AND gate? If both the inputs consist of 1, then the output would result in 1. In all other cases, the output would be 0. And for the NAND gate, which is a complement of the AND gate, if both the inputs consist of 1, then the output would result in 0. And in all other cases, the output would be 1. That's it for the NAND gate. Now let's talk about the NOR gate, which is another universal logic gate. It is similar to the OR gate. There is a bubble on the outside. The NOR gate is a combination of the OR gate followed by the NOT gate. It is also similar to the NAND gate, but here it would be followed by the OR gate would be followed by a NOT gate, which means let's observe the diagram. The A, B is the input and Y is the output. The primary one is the OR gate. It is followed by a bubble on the output side, which represents the NOT gate. If you observe the below diagram, secondary diagram, then you would understand what I am talking about. The truth table of the NOR gate is it also consists of the comparison of OR and NOR. Let's reminisce about what we said about the OR gate. If the input side consists of at least one, or both the inputs consist of one, then the output would result in one. In case both the inputs consist of zero, then the output would result in zero. And NOR gate is the complement of the OR gate, which means if both the inputs consist of 0, then the output would be 1. And in case one input consists of 1 or both the inputs consist of 1, then the output would result in 0. Let's talk about our third gate in the universal logic gates, the XOR gate. The XOR gate has a graphic symbol similar to the OR gate, except for the additional curved line on the input side. The output of this is 1 if any input is 1 and 0 when both inputs are same. We can express this algebraic function with AND, OR, and complement operations. Let's talk about the statements by observing the circuit diagram. A and B are inputs and Y is the output. And in the first statement, it is said that it is similar to the OR gate. Yes, the diagram is really similar to the OR gate. And there's only one difference, which is a curve on the input side near the AP. So it is easy to remember. The true table of the XOR gate is if both the inputs are same, then the output would be zero. If one input is different and the other is different, like 0, 1 or 1, 0, or uh, any other case for the triple one, the output will result in 1. That's it for the XOR gate. Now let's move on to XNOR gate. It is also pretty similar to the XOR gate in terms of graphic symbol, except for the additional bubble on the output side, which means the NOT, the complement of XOR. The output of this is 1 when both inputs are same and 0 in other cases. We can express its algebraic function with AND or in complement operations. Let's observe the truth table and the circuit diagram of the XNOR gate. Yes, as I said before, the XNOR gate is pretty similar to a XOR gate, apart from this bubble, which represents the complement of the XOR gate. The below diagram, primarily describes what I'm currently talking about, like AB as input, and this one is the XOR gate, and it is followed by a NOT gate, which gives a complement of the XOR gate. See the truth table to understand the difference between the both. AB inputs 0, so XOR gate would give us 0. And since the both the input values are same, the output would be 0. It is similar in the case of both the inputs being 1. We'd get the output as 0. Now, for XNOR gate, since it's the complement of XOR gate, the output would be 1 if both the inputs are similar. And in case both inputs are different, for XOR gate, we would get the value as 1, output as 1. And for XNOR gate, since it's the complement of the XOR gate, we'd get the value as 0. That's it. That's all about the digital logic gates and the universal gates. Thank you.